right. All right, so just so that we know where we are in terms of the class material, we are currently at about this point. This is going to be your next homework assignment. So today at the lab, you can start to do this homework assignment, but you can see it's not due until 1 week from today. So that means, if you want to focus on studying, you can kind of focus on studying. On the other hand, if you think you want to kind of spend some time to work on this one, and I can tell you, working on homework assignments like this is at least studying a little bit, because floating point representation is in the scope of exam 1. Okay, so even though it wasn't in the practice exam, it is still in the scope of the first exam. I will include everything up to the representation itself, and I might ask you questions about the conversion between a particular value and its double representation. But it's something that is doable by hand. I won't give you like pi and say, okay, give me all 53 bits of the mantissa. That would not be reasonable. But if I give you like 16, okay, that should be a pretty easy one to work on. Why is that the case? Why is 16 a particularly easy value to convert into a double representation? What is so special about 16? It's a power of 2. Any power of 2 is easy because it's going to have a 1 point, right? And then all zeros. So forget about the mantissa. The mantissa is going to be, the fractional part of the mantissa is going to be all zeros. Okay, so that takes care of 52 bits already. What about the mantissa? Well, 16 is 2 to the power 4, which means e minus 1023 has to be 4, which means e is going to be 1023 plus 4, which is 1027. Okay, so you just have to know how to represent 1027 as a base 2 number, as a binary number. It's 1024 plus 2 plus 1. You find all those bits, right? So you make an 11-bit binary number, stick it into bit 53 to bits, oh no, take it back, bits 52 to bit 62, and then depending on whether I say positive or negative 16, that determines the sign bit value. So that's a really, really easy value to work on. Okay. But right now, what we're going to do in class, so I'll show you what the assignment looks like first, and then we'll go ahead and look at some of the examples. Okay. So the preview of the homework assignment, which is what you will see later on in the lab, is you're going to have to copy a file first. Okay. And with every single class, I have at least one person who will send me a request to allow your write permission to the file. That means they did not follow the process correctly. Okay, so I'm going to show you once here. You right click on this to go to a new tab, okay, because otherwise you lose the main tab. And this is not a file that you can modify. Okay, this is just a file that belongs to me. So in order for you to make changes to this file, you'll have to do this. Go to File, go to Make a Copy. Okay, but don't just click OK, because most people who did that ended up having to ask me again how to make a copy. So don't click OK right away. So what you want to do is to specify where you want to make a copy to, because if you don't say anything, it will try to make a copy in the local folder, which is read only from your perspective. You won't be able to do it. So what you need to do is to click on Folder, and obviously in your case it's going to look different because if you keep backing up and up and up, it will eventually back up to My Drive. Okay, so by the time you get up to My Drive, which is your apps.losreals.edu drive, it will look different because you're not going to have the same subfolders that I do. So at that point, you can either use this icon here to create a folder just for that homework assignment, which is not necessary, or just specify my drive is the place where you want to put it. So let's just say that you want to put it to My Drive. Then you click on Select, and it will copy that file to your Google Drive. And then, because that's your local copy, you can then change the student ID and it will give you the test case that you are supposed to use for your homework. Is that okay? Are there any questions at this point about how to set up to get your test case? No questions? Okay. All right. Did I explain how to use CodeBlocks last time on Wednesday? I don't think so. Okay, that's fine. So what we'll do next is I will show you what you need to do here. So you'll have, once you have a copy, you just type in your student ID. Okay. So let me see. Okay. So let's say that's my ID, and the leading zeros will be deleted. I think most of you do not have a leading 0 in your student ID, but if you so happen to have a leading 0, just keep in mind that those leading zeros will be gone. And then they'll give you a number to test. Okay, so the green part is the only portion that you need to pay attention to. The rest is really just how I can get to this part here. So in this case, my test case is 4.846 E minus 1, 5. Okay, that is the string that you're supposed to put into the program to make a double representation of. Is that okay? All right. So then what you need to do is to go back to the question itself, and there's another file here. So this is a link to another file. This time is a zip file. And with a zip file like this, in Windows, you can just download it. But once you download the zip file, make sure you decompress or extract the content of the file, because until you extract it, you won't be able to actually work with those files. You can see them, you can view the content, but you won't be able to work with them. Okay. So you download it. I've downloaded it once already into my folder, so that's why it appears with a 1 here. So I will change it to my temp folder. So this will be the first time I download this particular file. And just keep in mind where you download the file. Now in my case, because I like to use command line interface, so I'm going to use unzip here. Okay, where is it? Oh, there you go, double. So I just use command line program to extract the content of the file. In Windows, all you have to do is to double click on the zip file or right click on it and then say extract. Okay, depending on the version of Windows, there might be some slight variation of the instructions, but I trust that you guys can Google and find out how to unzip a file in Windows. If not, I'm going to send you to cisp310, I think. That class teaches you how to use Windows. I'm hoping nobody needs to be sent to that class. Okay, so this is the content in the folder. Now, at this point, you have 2 options. One option is to make use of CodeBlocks, where you open CodeBlocks. Inside CodeBlocks, you have to open the CBP file, which stands for CodeBlocks project. The other way is just to recompile the .c files whenever you want to run the program again. So it all depends on how familiar you are with command line tools. If you say, I've been using Vim and GCC and GDB with my other classes, I feel comfortable with that option, then you can just go for that option. There's no need to install CodeBlocks. On the other hand, if you know what CodeBlocks is, you really like the GUI of CodeBlocks, and you go like, I want to keep using CodeBlocks. Well, fine, use CodeBlocks. If you have never been exposed to either one, okay, in other words, you have never used CodeBlocks and you have not used a command line tool to compile a program, then my first question is, how did you take CISP360? Because there has to be a third way or some other way for you to test run a C program. Okay, I think some other campuses might use Visual Studio. Has anyone used Visual Studio in CISP360? Okay, so that's probably why some of you may not have the experience of using CodeBlocks or the command line tool. So in that case, I think CodeBlocks resembles Visual Studio a little bit more than using the command line tool, but it's up to you, okay? So I'm going to show you where you can install CodeBlocks. To install CodeBlocks, you just open a new tab in your browser, use Google, and search for CodeBlocks. That looks simple, okay? It is pretty simple. However, there are certain things you have to pay attention to. Okay. The Wi-Fi is really slow. I don't know why. It's either the server, because my hard drive is not blinking at all, so it's not my computer being slow. And I can't, it's not responding. Let me try to refresh some other content here. Okay, that didn't take long. So it has to be their website, codeblocks.org, that is a little bit slow. Yep. To CodeBlocks. Okay, so it's a local CodeBlocks issue. So with CodeBlocks, when you download, there are several options to download. Make sure you download the version that includes MingW. Okay, MINGW. So that one you do need to include because that's where the tool set is coming in. So GDB, GCC, those are all the tool sets that are built into that particular build. Let me try SourceForge, because SourceForge is somewhat separate from CodeBlocks, and it might, yep, CodeBlocks is, SourceForge is up. And let's see if it has a separate download from here. Okay, user review, and let's take a look at files. Okay, so SourceForge may be a better way to go because at least it's not down. So with SourceForge, look up CodeBlocks, go to binaries, and then go to the latest version, which is 17.12. And of course, depending on your operating system, you'll click on one or the other. So since I'm assuming you're using Windows, click on Windows. And right here you have several options. And you want the one that includes MingGW. So the one that I'm highlighting does include MingGW. And it's a setup exe, setup executable. So this way it will guide you through the process step by step. The zip file, I think, will just unzip to a folder where all the tools are installed, quote unquote, installed in the folder, but it doesn't give you all the shortcut keys and stuff like shortcuts and whatnot. So I would just use this one, the third option from the top. Okay, are there any questions about where to get CodeBlocks? No questions? Okay, so the next question is, when I fire up your CodeBlocks, what does it look like and how do I get started with the project? Now, CodeBlocks is an IDE, and I have a locally installed version in Linux, but it should look pretty much the same in Windows. That part should not matter depending on the operating system. So when you open up CodeBlocks, mine is even an older version, 16.01, but for all practical purposes, it will work just fine. So from here, you go on File, and you click Open, and then you go to the folder where the double one is extracted. So I extracted it into a subfolder inside temp, and you can see all of these files. The CBP file is the one that you should open. So make sure you open CBP, the file with a CBP extension. If you install CodeBlocks in Windows, this is the one that will have the CodeBlocks icon, so it's easy to figure that one out. Okay, so once you open it, your screen should somewhat look like this. Okay, there is no need to change main. Okay, so main is already done for you. The program or the function that you need to implement is inside this particular file. So the name of the file that you need to modify is called exp10 to 2.c. Okay, exponent of 10 to exponent of 2. Are we doing okay so far with this? How to navigate in CodeBlocks? Okay. So you navigate to that file. You can always double click to open it. And you can see, just like most of the other IDEs today, when you double click on the source file, it will open a new tab. So this way you can kind of see what is inside a particular file. So in here, the text here actually describes what you need to do, but the homework has a better description. So I'm going to switch back to the browser to take a look at the homework description from here. So according to this, your code should take the struct number pointed to by parameter pn and preserve the value that is represented. So the value that is represented is the mantissa times 2 to the power of exp2, which is a member of the structure pointed to by pn as a pointer, times 10 to the power of exp10, which is also a member of the structure pointed to by pn as a pointer. Mantissa also is a member. In other words, we want to somehow get exp10 from a negative value to 0, okay? But you are allowed to change mantissa and exp2 any way you want to. Is that okay? So the following, the rest is just a description of what I would consider as the correct answer. The mantissa should end up as a value that has bit 63 set. In other words, it becomes if you double the mantissa again, it's too big. Okay, so this is the largest possible mantissa you can get, given the rest of the constraints. exp10 should be 0 when your algorithm is done. So when the function returns, I want the member exp10 to be 0 in the structure pointed to by pn. exp2 can be any integer, and it's signed. Okay, so that means it can go positive or negative. The represented value v should be preserved as much as possible. In other words, as you make changes to mantissa and exp2 and exp10, I want v to stay the same. Okay? That's basically the constraint of your homework. What you need to turn in is the mantissa and the exponent in 2. So those are the two things you have to turn in. So in the text area or HTML editing area, all you have to do is to kind of copy and paste from a debugger inside CodeBlocks into that text area. So I will show you what I mean by copying and pasting and how can we do that. Okay. So we'll go back into CodeBlocks right now, and the way to do it, let's assume I got this done already. Okay. So the way you do it is you put a breakpoint at the very end of this function. Okay, so this way you have a place to stop. Okay, because this program doesn't print anything. Okay, if it doesn't print anything, how do you get the output? There's no actual output, so using the debugger is the only way for you to get information out of it. And then there's one more thing that is really important to do, is to go to project, and then you go to set programs arguments, and then in here, okay, when the top part has selected debug, you want to specify program arguments. And the arguments you need to specify, now this part is very important. You have to specify -n, okay, or -n, a space, and then whatever string is presented in the spreadsheet. So let me go back to the spreadsheet first, because I need to know which one I'm supposed to work on. So you go to the spreadsheet, you look at the green cell, you can actually copy and paste. Okay, that works. So Control-C to copy, go back to CodeBlocks, and then paste here. Now the important part, very, very important, is if you do not specify a -n with no space in between, and then a space, and then a string here, your program may enter an infinite loop. So that means if your program terminates without hitting the breakpoint, or it does not terminate at all, it seems to be stuck in the loop, check your program arguments first, because that is the first thing that can cause the program either to exit right away without doing a single thing, or get into an infinite loop. Okay? So make sure you enter this. Now the other thing that is kind of important is if you use the lab computer in the lab, you kind of have to make sure that you save your project files onto your thumb drive, because otherwise the settings won't be maintained. So you got to be careful about that one. Okay, so I got everything set up. I haven't got a single line of code done, right? But I can still show you how you can capture the output of the program. And also, this is a good way to debug the program too, because you kind of want to know what the members have as values inside the structure. So I'm going to go run the program. So there are two ways to run the program. Do not use the green button. Okay, the green button means you're running the production version of your program, and it will bypass any way of debugging the program. So do not use the green button. Instead, go to debug, and then use start continue under the debug menu to start your program. Or if you want, you can use F8 on the keyboard as a shortcut. So the moment you press this, it will try to compile the program, build it, and okay, it did mention something about the debugger, but everything is okay at this point. Now the reason why I know it's okay is because you can see there's a little yellow triangle inside the stop sign. That means this is my execution point. The program has paused at this point. Okay, it has not executed this line. It has paused. So this is a time when I can enter a command here to print out what the structure looks like. Okay. The command here, which is under the tab debugger. Now I know sometimes people click on some other tabs and they lose track of these tabs here. Make sure that you're in the debugger tab in order to interact with the debugger. Okay. So what you do is you just say print, okay, whatever PN is pointing to, and that will print every single member of what PN is pointing to. That's fine, okay? Because what I need to grade your assignment, which is Mantissa and EXP2, is a part of it. Okay, so it's okay just to copy and paste these lines here into the text area that will appear when you are working on your homework assignment and you're done. Is that okay? Are there any questions about the mechanical aspect of what you need to do to turn in your answers? Yep, go ahead.
Actually, I guess it's not about checking the answer. I was just wondering where you went to set program arguments page.
It's under project and then set program arguments. So under projects and then set programs arguments. So that part is very important too, because otherwise the program doesn't know what argument it's supposed to process. But in this case, it makes sense because the number that we gave it was 4.846 E minus 15, which is really the same thing as 4,846 times 10 to the power of negative 18. Okay, so that part worked. The program gave you the right values to begin with. What your program needs to do is to make the mantissa really big. Okay, the exponent 10 should be 0, and then you adjust exp to so that the value represented would still be the same. Yes.
So you're essentially like reversing the process.
Reversing.
So Mantisha should be long instead of short, and exponent 10 should be 0. So basically, opposite of that.
Sort of. Okay. Are there any questions about this assignment? Okay, so where do we start? I mean, how do we approach this problem? So let me go back to this browser first. And unfortunately, I closed my YouTube already. So let's go back there because I want to see how much I have already talked about in terms of the process to do this. So we go back to videos, and it's going to be the one 5 days ago, which is this one. And then skip all the way to the end. Okay, so I think I talked about this already, how to, is that the video that, is that the class that, the content from last Wednesday? No? This is from the, huh? Oh, we went over the test, okay. So this is from the other class then. I should have named my videos. Let's see. Nope, that's not, that's 440. So that means it's going to be this one then. Yep, so that's the one because we went over the test. So 2 before this one would be the last time we talked about floating point numbers. I'm just looking back and see how much we have talked about. Okay, so we just talked about rounding in this class. Okay, that's fine. Alrighty. Okay. So let us go to the notes because I do want to show you where you can find more information about, okay, what about the mechanisms, how do we do this? So we go to floating point number representation as a class note. And what we are doing, this part is already done. In other words, I have written the parser already, and it's part of the program that I'm giving you. So you don't have to do the parser part. We have also done this part, conversion. We are starting to do this, okay? We're converting from base 10 scientific notation to a double representation. So this is what we're doing. 5.1 is already done, okay? So no worries about 5.1. It's already done by the time your function has control. So what we're going to do now is to do 5.2, but to be more exact, we're trying to do 5.2.1. So as far as your homework is concerned, the information is mostly contained in section 5.2.1 of the floating point representation module. All right. Okay. So the first thing I need to do is to kind of go back and explain rounding. The rationale of rounding and also the mechanism of rounding. Okay. So for that, I'm going to use my little tablet here and start up the command line to do that. All right. So the first thing is to talk about rounding, okay? But before we talk about rounding, the first thing we'll talk about is I'll just use an example. 29 divided by 10, but we take the floor of that, okay? So what do you think is the value of 29 divided by 10 and then you take the floor?
2.
It's going to be 2 because 29 divided by 10 is exactly 2.9. The floor of 2.9 is the largest integer that is less than the value. The largest integer that is less than 2.9 is 2. Okay. So this is just 2. But when you compare the actual value of 29 divided by 10 and the value that is the floor, the value, it has an error. Okay. So the error in this case, now if I have to give the error a sign as well, okay? So it's going to be minus 0.9 divided by 2.9. Minus 0.9 is the actual error, which is the value that it is supposed to be and the value that we can calculate, which is the floor of 29 divided by 10. And then it has to be divided by 2.9 because 2.9 is the actual value. So this is, if I use a percentage, this is the percentage of error. What if I were to multiply 29 by 8 first, okay? So 29 times 8 is, okay, I'm just going to do it on the side here. 1623, okay. So 232 divided by 10. And if I were to take the floor of that, it's going to be what? This went pretty easy. 23, okay? And what about the error in this case? The actual value minus what is reported. It's going to be a 0.2, right? The actual error is 0.2. and it is divided over 23.2. Okay, so in terms of percentage, which one is smaller? The top one or the bottom one? The bottom one. Okay, if I not only if I multiply 29 by say 256, okay, and then I divide it by 10, do you think the error is going to increase or decrease? It's going to decrease. Okay, so there's a reason why I want to make the number, the integer, as large as I possibly can before the division. Is that okay? But regardless of how big I make the numerator, okay, and still using 10 as a denominator, what do you think is the sign of the error? I know the magnitude of the error is going to decrease. What about the sign? Is it going to be the same or not? Hmm? It cannot be positive because because the floor of something is always smaller than the original thing. The floor of x is always less than or equal to x. Okay, there's a very rare chance that they are actually the same, but most of the time it's less than. Okay, so that's causing problems. So we have two observations right here. The first observation is we would like to maximize. Okay, maximize the numerator. The reason why we want to maximize the numerator is to decrease the error. Okay. And then the second observation is floor always errs on one side. In other words, when you look at the error, it's always being too small. Okay. The floor of a division by 10 is always smaller than or equal to the actual value of the division. Is that okay? But that's bad, okay? The first one we can kind of deal with, okay? We know how to maximize the numerator. But the second one is a problem because if we keep flooring, okay, after every single division, then in the end, and we keep doing this multiple times, then the end result is going to be quite a bit smaller. The error is going to, because it's always leaning in the same direction. It's kind of like, you have an alignment problem with your car, okay? So it's always pulling to one side, and then the moment you let go of the car, okay, it's going to veer off to one side, but it will veer more and more and more, okay? Because it's changing the direction all the way to only to one side, okay? So we want to be able to fix this problem. So now we look into rounding, okay? So we look into rounding. So rounding, the round of x is one way to compute that is to add 0.5 to x and then take the floor. I think we talked about this last time, okay? So this is a way to do it. And the nice thing about rounding is sometimes the error is positive and other times the error is negative. And it's 50-50, okay? Probabilistically speaking, when you perform rounding, half the time the result is just a little bit too much, and half the time the result is just a little bit too small, okay? So that's good because what we like about rounding is it's not only skewing to one side, it kind of balances off. The errors will tend to balance off. But we want to know how to do rounding because flooring is easy. Integer division itself gives you the floor function. Okay, it's built into it. Okay, when you have integer division, it only gives you the floor of the actual result of the division. What about rounding then? It seems like rounding is a little bit troublesome because the first thing we need to do is to add 0.5 to whatever we are trying to round, which means, hey, we need floating point calculations to do this, which kind of defeats the whole purpose of the assignment. Okay, so in the assignment, you cannot use any floating point number calculations. We can only rely on integer arithmetics to do it. Okay, so how do we do it? Fortunately, the thing that we are rounding is always the result of dividing something by a base. Okay, so we'll say this is, I'll use w here, just so that we don't use the same letter x. So how do we do that? Well, kind of the same thing. W divided by b plus 0.5, take the floor of the entire thing. But then that also becomes w plus b divided by 2, the whole thing divided by b. What if I tell you b is always an even number? What if b is either 2 or 10? Well, if b is either 2 or 10, then b divided by 2 is going to be a whole number, and it's always going to be exact. Oh, can we perform integer addition without losing anything? Yes. Okay. Can we divide it by another number and then take the floor using integer division? Yes. Oh, okay. So this whole thing can now be done using entirely integer addition and integer division, which is great because now we have eliminated the need to make use of floating point numbers. Is that part okay? All right, cool. So at this point, we have explained two things. One is why we want the numerator in the division, in the fraction, to be as large as possible because we want to minimize error. And then the second thing is we need to do rounding. We cannot just take the floor of a division. We want to be able to round it because we don't want the error to bias on one side. So are we good on those points? Okay, all right. Okay, so now I'm going to give you an example. Okay, so let's just say that we want to work with 29. Okay, because we used 29 before, we'll use it again. So we start with 29, and we'll just say that the mantissa is 29, and exp10 is negative 2, and we want to figure out, how to represent 29 times 10 to the power of negative 2, which makes it 0.29. So how do we represent 0.29 as a double? Where do we start? Okay. Well, in theory, it's really simple, because in theory, what we need to do is we want to get rid of exp10. And to get rid of exp10 when it's negative to begin with, that means we have to add something to exp10. But we don't want to change the value represented, right? Whenever you add 1 to exp10, you have to make up for the multiplication by 10 by dividing the mantissa by 10. Is that okay? So that means if I could do that, okay, which I cannot, okay? If I could, I would just say that this is the same thing as 2.9 times 10 to the power of negative 1. And then it's also the same as 0.29 times 10 to the power of negative 2, to 0, okay? And I'm done. But I can't do that. I cannot do that because 2.9 is a floating point number, okay? 0.29 is also a floating point number. I can't do that, okay? Because I need the mantissa to stay as an integer the entire time. Okay. Well, if we cannot do something like this, what about that rounding trick that we did? So that means 2.9 will be rounded to 3, and then 0.29 will be rounded to 0. Would that be okay with you? If someone is to say, I want you to give me the floating point representation of 29 times 10 to the power of negative 2, and you tell me it is 0, is that okay? If I were NASA, I would definitely not hire that person. Where's that Mars probe again? I think it's under the ocean on Earth somewhere. Because of the rounding issues, right? You fire the rocket, it lands in the Pacific Ocean. But according to this math here, it's mission accomplished. Okay, so we don't like it this way. So what are we going to do? What happened here? What resulted in this problem? It's the error of rounding, right? When you divide 29 by 10, even with rounding, the error is a little bit, but not too bad, because 2.9 and 3 is kind of like, yeah, that's only about 3%, right? But when you round 0.29 to 0, that's the entire error. The whole thing that you want to represent becomes the error, which is not acceptable, right? Okay, so how do we fix this problem? Well, we don't want to do any division yet, okay? We want to make the mantissa as big as we possibly can. So what do? We go like this, okay? So the next thing we say is, what if we multiply the mantissa by 2, okay? So the mantissa is now 58. That doesn't change anything about exp10, so that would still be -2. But if I multiply the mantissa by 2, that's going to change v unless I do something to counteract that, right? So what do I need to do to counter doubling the mantissa? I need to divide it by 2, but I can't divide the mantissa by 2 because the whole point is to make it bigger. But I have one more thing I can play with inside the structure. What is that? The exponent of 2. Very good. So I can now say, we can make this a -1 now. It used to be 0. Now it's -1. So if you think about it, do these two things will represent the same value? 29 times 10 to the power of -2 versus 58 times 2 to the power of -1 times 10 to the power of -2. Would those be the same value? Sure, they're the same value. But I look at 50 and go like, can I make it bigger? Because remember, mantissa is a 64-bit unsigned integer. Okay? And 58 doesn't seem to take up all 64 bits to me. How far do we have to go? Okay, so the next one is the mantissa becomes 2 times 58, which is 116. exp10 stays the same because we are not going to subtract 10. Excuse me, we're not going to divide it by 10 until we say, yeah, we can't make the mantissa any bigger. Okay? Would that be okay? Are we still representing the same value? Yep. So the next one is going to be 232, and then 464, and so on. Okay? So that's going to be a pretty boring process. When do we stop? How do you know mantissa cannot be any bigger? Okay, so that's a good guess. Okay, but so let's say that is the case. Okay, so we'll just say that we'll do this as long as the mantissa is less than. Okay, so we'll put a question mark here. We'll just say 2 to the power of 63, and we'll put another question mark here. It will get you close, okay? Using this condition will get you pretty close to what we need, but not exactly, okay? All right. For now, we'll just leave it like this, okay? And then what do we do about the mantissa? Because I'm going to end up with a pretty negative exponent exp2, but the objective is, go ahead.
So probably like if we want to go to like 2D63 was like the whole range. So if you want to like compare it to a number that's like that might be bigger than the range, so it may overflow. So we may probably like compare it to one less than like 2D60. So it's gonna be like is it less than or more than half the value of 2D60?
Right. So we want to compare to about 1/2 of the largest possible unsigned 64-bit number value, so that the next, if you double again, it's going to break it. Right. Okay. But then what do we do about mantissa? What is the whole point of this exercise? Why are we making mantissa so big? So that we can divide it by 10, right? Okay, so we will divide it by 10. So now we say the mantissa is the mantissa divided by 10. But this is integer division, which means a floor is built into it, right? But wait, Tech, you just mentioned something about taking the floor of a division has a bias always in one direction, and we need to do rounding. Okay, so how do we do rounding again? We have to add 1/2 of the numerator before we actually perform the division. Okay, that seems pretty obvious. What is 10 divided by 2? It's just 5. Okay, it's just a constant. Okay. So we cross this out, becomes just 5. That's what we're going to do. We are going to change the mantissa, so it becomes whatever it was plus 5, and then the whole thing divided by 10. which is basically kind of just like dividing by 10, except for rounding. This part is only done for the rounding. Remember, mantissa is going to be a pretty huge number, okay? Adding 5 before divided by 10 is not going to change the result too much. It will change it a little bit. It will kind of give it a nudge, but it's not going to be too much, okay? And if I'm dividing the mantissa by 10, what do I need to do to compensate for that division by 10? Increase the exponent of 10. Okay, so we need to do something like that, right? Because exp10 was negative 2 to begin with, now it becomes negative 1. And then what do? We have to go back and keep doubling the mantissa again. Because the division by 10 is going to make the mantissa not quite as big as it could have been at that point, and that's why we have to keep doubling it again until we hit that limit. So this is how we can minimize the error involved in the process and also make sure that it is not biased. So are we good with at least the idea of what we need to do in the program? More or less? Okay? So now we get back to the question mark, okay? Because once we understand what we are going to do with mantissa, we can now go back to this part and go like, okay, so what do we need exactly when we compare the mantissa as we keep doubling it, okay? Well, it has to do with what we need to do with mantissa afterwards. So we need to make sure that mantissa plus 5 is no more than what a 64-bit unsigned integer can represent. Is that making sense? Making any sense? Okay. So that means when we keep doubling the mantissa, we have to stop as soon as the mantissa is greater than or equal to the largest possible integer minus 5 and then the whole thing divided by 2. Okay, so I just said something, let me write it down, okay? So I'll just write it down like, max u int 64. I'm going to use this to represent the largest value you can represent using a 64-bit unsigned integer. Is that okay? So the idea is we want to leave enough room to do the plus 5 before we divide it by 10. We also want to make sure that when we double mantissa again, it's going to be too much. So how do we work out this math? This is the first thing we need to take care of, okay? So we have to say that, right? But that is not the actual limit we're going to compare. This is going to be the double of the maximum value of mantissa before we have to stop. Is that okay or not? If the mantissa is greater than or equal to 1/2, it's greater than, excuse me. When the mantissa is greater than 1/2 of this, we have to stop because the next doubling is going to cause problems either with this or we just cannot represent the double of the value itself. Okay? So we have to divide it by 2, like that. And then the comparison to this mantissa is still less than. As long as the mantissa is less than this amount, we're still good. So we'll still use a less than here and then plug it into this place. Is that okay? All right. So once again, I'm just going to explain how this works, okay? When mantissa is greater than or equal to this amount, that means the next doubling is going to make the value max underscore int64 minus 5 greater than that amount. Okay? When it's greater than that amount, what's going to happen? We won't have the room to do the plus 5. So that's why. And I think equal to is fine. So less than or equal to instead of less than. Because when mantissa equals to this amount, we can still double it one more time. Because when we double it, it becomes max u in 64 minus 5. We take that value, we add 5 to it, so that the numerator becomes really just max u in 64, which is okay. It's the last largest value that can still represent it in 64-bit. Then we divide it by 10, everything is good. So less than or equal to is correct here. Because otherwise you'll miss one value. There'll be like slightly suboptimal. Okay, next thing. How do we find this thing here? How do we find the maximum value that a unsigned 64-bit integer can represent? There are many ways to do it. There's the painful way to do it, and then there's a not so painful way to do it. I can think of at least 4 ways to do it, including the painful ones. So which ones do you guys want to explore first? Let's do the painful way first, okay? The painful way is to go by the definition. So I'm gonna, okay, so we want to find out what is u in 64, what is the maximum of that, okay? So the painful way is to look at the actual definition. So the definition is this is 2 to the power of 64 and then the whole thing minus 1. And of course you can use a calculator to do it, but your calculator may not give you the exact value. Why do you think your calculator may not give you the exact value? Well, the subtract 1 is not the problem. The problem has to do with the precision. So we are talking about 64-bit as precision in this case. Even a double only has 53 bits for precision. The other bits are for the exponent and other things. So you only have 53 bits of precision. So a double itself cannot represent the precision that we need here. How many digits do you think this is going to look like? Okay, do you guys know how to guesstimate, like the number of base 10 digits given the number of bits? No? Okay, I'll show you this really really cool, quick trick to do things like that. Okay, so to guesstimate how many digits you need without log and exponent or calculator, this is how you do it. You basically say 2 to the power of 10 is about the same thing as 10 to the power of 3. Okay, because 2 to the power of 10 is 1024, and 10 to the power of 3 is 1000. We call that close enough, okay, for estimation purposes. So when you look at 2 to the power of 64 minus 1, which for all practical purposes is 2 to the power of 64, then you go like, wow, that has got 6 of these things, right? Well, 6 of those things will give you 18 base 10 digits already. And that's only taking care of 2 to the power of 60. You still have 2 to the power of 4, which adds 2 more digits to the whole thing. So we are talking about 20 digits in base 10. So even if you can get to the exact value in base 10, it's going to be a 20-digit thing that you have to type in to your program. That's why I said it's painful. Okay? Okay, so first method, trying to specify that value in base 10 using a calculator or using a spreadsheet is either impossible because the internal representation cannot deal with it, or it is extremely painful. Okay? But if somebody wants to do it, hey, go ahead. Okay, so second way is easier. The second way is to look at this from the hexadecimal perspective. In other words, we look at this value and we go like, does it have a particular bit pattern? What do you think? So you try to think about this, okay? Think about 2 to the power of 3 minus 1. Okay, that's 2 to the power of 3 is 8. 8 minus 1 is 7. What does 7 look like as a binary number? 1, 1, 1. Okay, ones. Okay, very good. Okay, let's see if this works when I plug in, say, 8, right? 2 to the power of 8 minus 1. 2 to the power of 8 is 256. Minus 1 makes it 255. what does 255 looks like as a binary number? All ones, 8 of them, right? Okay. So do you think 2 to the power 64 minus 1 has a particular pattern? And what pattern would that be? All ones. How many ones are we talking about? 64 ones. 64? There are 64 ones. So that means it's going to look like this, okay? 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, okay? I'm using the dot, dot, dot because, it's not fun to write 64 ones, okay? So we'll just say that there are 64 ones. But you can't really enter a binary number in C. C has no prefix to deal with binary numbers. Now GDB does, but C and C++ do not, okay? So go like, okay, how do we enter this as a value? Do you guys remember hexadecimals? So in hexadecimal, every 4 bits becomes 1 hexadecimal digit, and 1111 is F. Okay, that looks doable. So you have 0x, okay, which is the prefix in C and C++, to basically mean the rest is a hexadecimal number. Then it's just 16 Fs, right? Because there are 64 ones, 1 F accounts for 4 ones, so 64 divided by 4 is 16. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's one way to do it. I call this probably the next most painful way to do it. But it's a lot better than entering the decimal version, because the decimal version has digits that are all over the place, and there are 20 digits, okay? This one has got 16 digits, and they're all the same pattern, okay? If you know how to use VI, for instance, you can type this in one single command, okay? You just say 0x escape I, take it back, 0x escape 16 if escape again, okay? So that will type all 16 Fs for you. Because in VI, you can specify the count of doing something, so it will automatically do something based on the count that you specify. Okay, but that's still kind of painful. What is the easiest way to do this? Well, okay, subtracting 1 is not going to work. The reason why it's not going to work is because when you are dealing with 64-bit number, 2 to the power of 64 itself cannot be represented using only 64 bits. So it was a great idea if we could do that. If we have 128-bit numbers, for instance, then we can kind of work that one out. Okay? Okay, what else? What else can we do about this situation? I'll call the next one not so painful, but really tricky. Okay, I'll give you the whole version of this. You go like, it doesn't make any sense. It's self-contradictory, right? Because -1 is obviously a signed number, signed value, and then I'm using the typecasting thing called uint64_t to try to typecast -1 into the largest possible value in an unsigned 64-bit number. The whole thing is just filled with contradictions and dilemma. Okay. But why do you think it's going to work?
I mean, you're taking essentially the -1, it's going to roll over, right? Like you're casting it, it's going to be.
Yep.
If you subtract 1 from 0, it's going to be the max number.
Yep. Because if you number the number wheel, -1 really has the same representation as the largest unsigned representation. That's what that is doing. But it's very tricky, okay? If somebody were to look at that code and go like, what is that? Oh, that's what it's doing, okay? Now, I'm a little bit dubious about this myself, so we'll give it a try. Okay, we'll double check to see whether it actually works or not. There we go. And all we need to do is to get into GDB, and we say print -1. Okay, print -1 is just -1, and then we're gonna print unsigned. I think it's long to specify 64-bit. And there we go. Does anyone want to count the number of digits here? I'll do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yep, that's it. It's obscure, okay? Because if you were to use this as a constant in your program, the next person who's going to inherit your program is going to like, what is that? Unless it's one of your classmates in the same semester. Because I bet you next semester you would have forgotten what this means. Yep.
It's kind of like aiming at an address. You know where the number you want is, so you just take the shortcut.
Yep. Yep. So that's definitely a shortcut. Okay, so if it's a shortcut, even though it looks really simple but not recommended, so what is the best way to do it? What do you think? Well, let's ask Google. uint 64_t maximum value. Okay. And it suggests us to read wikibooks on stdint.h. That sounds vaguely familiar to me. And it should to you as well. So we click that. And you go like, whoa, that is a pretty huge document. What do we do about this? And you look for uint64. And you keep searching. Oops. Okay, it's got some maximum here. Oh, right there. Okay, I didn't see it the first time, but now I see it. Right there, uint64_max. I mean, I cannot remember the name of that. I kept saying, max uint64, right? But turns out it's all uppercase uint64_max. So if you have pound included standard int.h, this is the proper way to refer to the largest possible value as a 64-bit unsigned integer. So as promised, I delivered the 4 ways of specifying the same constant. Base 10, 20-digit, kind of painful. 16 hexadecimal digits, next most painful but manageable. Okay. Unsigned, long, the whole thing, and cast. Use that as a typecast to -1. Totally obscure, gets the job done, but doesn't quite say what it really is. And now we have the exact macro that we need to refer to that is predefined in the header file that is already included in the program. Is that okay? All right. So do we have any questions about how to do your homework assignment? Have I explained everything that you need to know to do this homework assignment? Okay, so we get back to this, and then we kind of reverse back to the example that we have. Okay, so we just kind of focus on this one. We start with 29 as the mantissa and a -2 as exponent of 10, and then we keep doubling the mantissa. We keep doubling, as long as it is still less than or equal to. Now remember what this is supposed to be now. Uppercase uint64_max, okay? -5, the whole thing divided by 2, okay? As long as mantissa is still less than or equal to this, keep doubling it. But every time you double, you have to do one thing. Every time you double mantissa, you have to decrease or decrement exp2 by 1. Because the value being represented should be the same. Is that okay? When you get out of the loop, what do you know? When you get out of this loop, you know that the mantissa is greater than max u in 64 max minus 5 divided by 2. What are you going to do with that huge number? Add 5, the whole thing divided by 10, that becomes the new mantissa. But because you're dividing the mantissa by 10, you have to add 1 to exp10. And then what do? Do the whole thing again until exp10 is 0. Exactly. So without actually spelling out the loops in C, I think I'm giving you the logic to do it. Are there any questions about this process? Yep.
Does it have to take, do we have to consider that exp10 can be positive or will it
Nope. In this particular assignment, it is only negative. The next assignment we'll deal with when it's positive, but that's next week. So are we good so far? Okay. So assuming that it is okay at this point, I'm going to move on in terms of the class notes to what if it's positive to begin with. Okay, so let me give you a new scenario. Okay, so this time the mantissa is, okay, let's make it 29 again, and exp10 is positive. Let's call it 2. Okay, so the value that I want to represent is 29 times 10 to the power of 2. Well, guess what? It's a pretty easy one to deal with. Why is that the easy one to deal with? Yep, okay, so because the objective is to make exp10 0, right? So that means, okay, if I want to decrease exp10, I have to multiply the mantissa by 10. Okay, so 29 times 10 to the power of 2 is really the same thing as 290 times 10 to the power of 1, which is the same thing as 2,900 times 10 to the power of 0. Done, not. What am I missing? I need to make the mantissa as large as possible. Okay, now why do I need to make it as large as possible? We are not even dividing it by anything. Why do we need to make it bigger? Sorry? But we are not dividing, so there's no quote-unquote error here. In the representation of a double, how many bits are in the mantissa? 53 bits, of which 52 are actually represented. That is why. We still need to make up for all of those extra bits in the mantissa because they're all individual bits inside the double. Okay? So that may be easy, okay, because it's just like, okay, then we just do a whole bunch of bit shifting until it is done. What about this guy? Let me see. I have to think about whether it's still doable as a double. Yes, it's still doable with a double. So what about this one? We can't do that anymore. Because if you multiply 29 by 10 200 times, that's going to overflow a 64-bit number. Because multiply by 10 once is adding one more digit. So at the most, with 29, which is taking up 2 digits already, you only get about 18 times that you can multiply it by 10, okay? So even 20 is not going to work. So let me just kind of erase this to be 20. There we go. So that is too much already. So what do you do? When do you know that you cannot multiply the mantissa by 10 anymore? Because another multiplication by 10 is going to bump it over the largest value that you can represent as a 64-bit unsigned number. Wait, we heard that phrase some moments ago, maybe about 5 minutes ago. Okay, so we got some logic that looks like this. As long as the mantissa is less than or equal to something, what we're going to do here is to say mantissa is mantissa times 10 exp10 is exp10 minus 1. But the question is, what is in this big mess here? Well, what do you think? Mm-hmm. Is u int 64 max minus 1, the whole thing divided by 10. Divided by 10. Let's see. Yeah, divided by 10 because, so what the way you think about it is, what if mantissa is exactly that amount, right? So when the mantissa is exactly this amount, then the next multiplication by 10 is going to bump it over, okay? Then what about the minus 1? Why do we need that extra minus 1 here? What do you think? Because if you run out, what do you need to do? Okay, so let's say you go through this loop and you handle 18 of 17, okay, 17 of the exponents by 10. You still got 3 more to go. What are you going to do? Then you might think, but I have already maxed out the 64-bit unsigned integer. I can't handle this anymore. But you can. We can make room. How do we make room? We haven't really used the exponent of 2 yet. So what do? We divide the mantissa by 2 again and again and again until there is room to multiply by 10 again. Okay? But when we do a division by 2, wait, division by 2 using integer math is going to have errors. Okay? And it's also by default a floor function. So what do we do again? We don't like floor because it is biased. So how do we make it not biased again? Add 1/2 of the numerator, then divide it by the numerator, right? The numerator this time is 2. What is 1/2 of the numerator? 1. So we have to add 1 to the mantissa before we divide it by 2. That's why we have to have this little minus 1 here, just so that when the mantissa is exactly this much, we're still good. Is that okay? So we keep doing this, and then when we get out, then we have to make room. So how do we make room? Make room is saying as long as the mantissa, okay, let me think about how to specify that. Okay. I just clicked the wrong button. Okay, so as long as the mantissa is still too much to perform another multiplication by 10. So as long as the mantissa is still greater than u int 64 max divided by 10, what do we do? Okay, so if the mantissa is greater than u int 64 underscore max divided by 10, that means I can't go back to this loop yet, because the moment I multiply the mantissa by 10, it's going to overflow at u int 64. So what do I need to do to make room again? I just mentioned that a little bit earlier. Divided by 2, exactly. But it's not just division by 2, because we have to take rounding into consideration. So mantissa gets the mantissa minus 1 in this case, then you divide it by 2. And then we have to adjust something, because every time you divide it by 2, we have to do something with the exponent. exp2 needs to be incremented or decremented? Incremented, exactly. There we go. But Tech, this doesn't look like C code to me. Well, that's your job. It doesn't look like C code in many ways. There's no such loop as long as, okay? Less than or equal to doesn't look like this, okay? You don't really have a variable called man or exp10 or exp2. Those are members of the structure pointed to by the parameter. But I trust that your C knowledge should be sufficient to handle that part. This is not even due next week, and this is not even assigned yet. But once you're done with the assignment this week, this one is easy. Kind of the same thing, except flipped. Yep. So are we doing okay so far with the homework and your understanding of what a double is and how to do the conversions? More or less? Okay. So Wednesday is the exam. Okay, so if you have any questions about the exam, go ahead and ask me. And I do want to give you just a preview of what is after the exam. It's always good to keep an eye on what we're going to do after this. We're almost done with the whole thing about physical states, gates, and numbers. So we are almost done with that. And the next one to start with is D flip-flop and other memory devices, basic memory devices. So on next Monday, we'll go over the test. Hopefully it doesn't take the entire class, but after we go over the test, we'll start with D flip-flops and other basic memory devices. And once again, these can all be simulated in Logisim, which is kind of cool because you can make up the gates and then you actually click it and see how it works. All right. So today at the lab, there's no actual passcode. You can basically get started with setting up CodeBlocks and get started with experimenting with the program. It's not due today. It is due next Monday. All right. I'll see some of you at the lab.